Hello everybody, this is Mr. Johnson, and we are going to be going through the EL3 notes. Fairly short, fairly quick, but you have to know a few tricks in order to get this target. This target EL3 is for solving exponential and logarithmic equations. So we've graphed them, we've translated them back and forth, now we are going to be solving them. So remember, that word equation means that there is going to be an equal sign in our problem. So you always know when you're getting one of those if there's that equal sign. So first off, how can you tell if an equation is exponential or logarithmic? Well, it's fairly easy. Exponentials will have an exponent, and specifically what you're looking for is a variable up in that teeny tiny exponent spot. Logarithmic equations, like hit you over the head with a 2x4, they have the word log in them. You can't miss it. So logarithms have log, exponentials will have an exponent. Now, here's the harder question. When is it advantageous to solve using exponential form versus when is it advantageous to solve using logarithmic form? Well, that answer, and I'll let you get this down here in a second, exponentials are easy if the bases match up to be the same. If you can get them to have the same base, exponential form is the way to go. Whereas logs, they're a little bit better if the bases aren't related. So if you have 3 to some power versus 2 to some other power, you can't get 3 and 2 to be the same, so logarithms would be the way to go. Go ahead and take a minute, copy this down, and then we'll get rolling on some questions so you can see this in action. Question number 1 says 3 to the x equals 27. Now, if you recall, we need to always be looking out for numbers that are perfect, that can be rewritten in different ways. 27, if you break it down, is just 3 times 3 times 3. Another way to rewrite that is 3 cubed. Now, if I put 3 cubed in the place of 27 and I rewrite 3 to the x power, what do you notice about the bases? In this problem, both of the bases are the same. 3 to the x equals 3 to the third. So the only answer that can happen here is that the exponents have to be the same as well. So x has to be equal to 3. Think about the logic of this problem. 3 to what power equals 27? Well, we know 3 to the third power equals 27. So that checks out. That makes sense. And just like that, you've solved your first exponential equation. They'll get a little bit harder, but that is the idea behind them. So let's look at problem number 2. It says 1/4 equals 4 to the 2x. Ugh, this doesn't look quite as nice as the first one. Well, you have to know a little bit about 1/4. 1/4 can be written with a negative exponent. It is actually 4 to the negative 1. Think about 4 if it jumps to the other side of the fraction. It's up here now, but if it jumps to the bottom, that's going to be 1/4. So 4 to the negative 1 equals 4 to the 2x. All I did is I rewrote that part down there. Now, what do we notice about the bases? The bases happen to be the same. And if the bases are the same, then your exponents must be the same as well. So we can basically just take this and say negative 1 equals 2x. We're just dealing with the exponents and the teeny tiny numbers that are up there. And solving this is a breeze. Divide by 2, divide by 2. X equals negative 1/2. Bam! There we go. So solving exponentials isn't hard so long as you can get the bases to be the same. So you need to be on the lookout for that. Let's try question number 3. 4 to the x equals 32. 32. I don't know if there's really a nice way to rewrite 32, unless I break it down. It's certainly not like 4 squared. 4 times 4 is 30. Sorry, 4 times 4 is 16, and if I multiply that again, I can't get 32. But if I break this down, 16 and 2, 16 is 4 and 4. I got a bunch of 2's. I can rewrite 32 as 2 to the 5th power. Well, that still doesn't help me, because I have 4 to the x power and 2 to the 5th power. So what should I do? Well, 4 actually is a perfect number, just like 32 is kind of a perfect number right up here. 4 can be rewritten as 2 squared. Well, if that is 2 squared, where did the variable go? We can't just have it disappear. Guess what happens? It gets drug along and it connects with the exponent that was right up there. So we had 2 squared, but then we had an x that has to go along with the 2 in the exponent position. So this really looks like this. 2 to the 2x equals 2 to the 5th. Well, the bases are now the same, so I should have the exponents be the same. 2x equals 5. That's what was in the exponents. So dividing by 2, x equals 5 halves. 2.5 if you're a decimal person. Now there are other ways that you could do this. You could, in fact, use logarithms. And that's what we're going to see here. Logarithms really start to work in our favor. So you can stay in the same base format, but if I were to rewrite this, 4 to the x equals 32, rewriting this in log form is kind of cool. Remember, if you're going to translate to log form, you have to write the base down here, and the base with the exponent is 4. That's taken care of. Then I would go ahead and I put 32, and then I write whatever my exponent is, which is x. If there is a variable in the x position, logarithms will help you solve it and help get that variable out from the exponent. Notice here it's just sitting on the regular ground. If I were to put this into my calculator, guess what number I would get? I would get 2.5 equals x. This and this, they are the same answer. 5 over 2 and 2.5. We are going to start to do our problems more along this vein of thinking, using logarithms to our advantage. Big question here, how do we solve exponential equations? Well, we can solve them using logarithms. Let's go ahead and let's see what happens with question number 4. We might use exponentials, we might use logarithms. It depends on what we get. So to start off, we have a bunch of stuff here. 81 equals 3 times 5 raised to the x minus 7 power plus 7 at the end. We got to work out of some of this crud. So let's get rid of that 6. Subtract 6 from both sides. 81 minus 6 is 75. Rewrite the right-hand side. 3, 5, and x minus 7. Teeny tiny up there. Getting rid of the front 3. You have to divide. So I'll go ahead. 75 divided by 3 is 25. What's left over is 5 raised to the x minus 7 power. Now, if you are smart, you might not use logarithms here because 25 is a perfect number. 25 is 5 squared. Notice what has happened with my bases. Anytime that you can do this, I would encourage you to, because you will save so much work. 5 to the second power and 5 to the x minus 7, those have to be the same exponent. So I'll just go right up over here. 2 is the first exponent. X minus 7 is the other exponent. Now it's just a simple problem where we have to solve. Add 7, 9 equals x. I could have gone ahead. I could have done logarithms in this position. If I go ahead and do logarithms, I would have to have log with a base of 5. I would put the answer, which was 25, right up there, and that's going to be equal to the exponent, which my exponent had x minus 7. If you go ahead and solve this out, like what we did in the second target, you're still going to get 9. It's just that this way has more work to get to x equals 9 than these few steps up here. So keep that in mind when you're solving your problems. Different roads to go, hopefully leading you to the same answer. Let's use that with question number 5. Question number 5 says 1/4 10 to the x power equals 25. Well, how do we get rid of a 1/4 in front? You could divide by 1/4, but one thing I like to do as well is multiply by its reciprocal. Dividing by a fraction and multiplying by a reciprocal, they do the same thing. So 1/4 and 4/1 cancel each other out. That means this guy needs a 4/1. 4/1 is the same thing as 4. So think about 25 times 4. 25 times 4, if you have 4 quarters in money, that's 100. 10 to the x equals 100. 100, if you're smart, is 10 squared. 10 to the x equals 10 to the second. Well, that just means my x has to be 2. and we're solved. Logarithms would work, but logarithms have a little bit more numbers in them. Question number 6 says 9 to the x equals 27. Well, 9 and 27, they're not the same thing. But there are different ways to rewrite it potentially. So if I think about 9, 9 could be rewritten as 3 squared. But again, it's to the x power, so I need to have an x up there as well. 27 is just 3 times 3 times 3, which is 3 to the third power. Now, since the bases are the same, I know that the exponents have to be the same. So 2x and 3, just go ahead and solve, divide by 2, divide by 2. X equals 3 over 2. That's just 1.5. All right. I typically would leave my answer as a fraction, but you can put decimals. This isn't the only way. If you see that 9 and 27 are incompatible, that their bases are not the same, maybe try to use logarithms. So in this case, you would put log of 9, 27, and then equals whatever the exponent is, in this case, just x. If I do the change of base formula, because your calculator can't do base 9s, it is going to look like this. Log of 27 over the log of 9. When I enter that in my calculator, guess what I get? 1.5. Just to show you, in case you don't believe me, log 27, close my parentheses, divided by log 9, close my parentheses, 1.5. Either way you want to do it, you'll get the right answer. Last couple of problems on the front page. Number 7, 250 equals 2 times 25 to the x power. Well, got to get rid of that 2 first. It's causing problems. 250 divided by 2 is 125. Next, go ahead and rewrite it as 25 to the x power. Notice 125, 25, not the same thing. So we could use logarithms. That sounds fine. So you could do log base 25 and 125 in the parentheses equals whatever the exponent is, which is just that variable. If I'm going to do this in the calculator, I have to do change of base. So remember, the big number goes up top, the small teeny tiny number goes down on the bottom of the fraction. So log of 125 over the log of 25. That's equal to x. Go ahead, slap that in your calculator. Log of 125 divided by log of 25 equals, hey, that's weird, 1.5. So x equals 1.5. There is a way to do this using exponents. Let me show you. 125 is a perfect number. It's actually a triple brancher. It's 5 times 5 times 5. It is 5 to the third power. 25 is also a perfect number. It is 5 squared. Don't forget that you had a variable up there, so put it with your exponent. Since the bases are the same, the exponents will have to be the same. So I get 3 equals 2x. Divide by 2, divide by 2. I get 1.5. 3 over 2. I get the same answer either way. Question number 8. There's definitely only one easy way to do this. 6 to the 2x equals 21. 6 and 21, there is no way to get this special relationship that 125 and 25 had. They are just at odds. So I'm going to actually have to use the logarithm technique. So that's pretty easy. Log with the base, which happens to be 6. I put 21 inside, and I get my exponent, 2x. So to put this in my calculator, I have to do the change of base formula, log of 21 over the log of 6. That's equal to 2x. Recall, to get rid of the 2, I divide. Dividing by that 2 is on the bottom of the fraction. So when I go ahead and put it over here, it is also on the bottom of that fraction. Just kind of slides right in there. So these are the same idea. If I put that in my calculator, so log of 21 divided by, I need to trap 2 and log 6 down here. I'll trap all of that, or else it will divide by 2 and the log of 6 is just going to escape. So 2 times log of 6. Close my parenthesis for the logarithm, close my parenthesis for the cage that wraps them together, press enter, whew, and that It's not a nice number. We wouldn't have been able to do that with exponents. So 0.8495. I do like 4 decimal places with these just to make sure that you've done everything correctly. You don't have to round or anything like that. Just write out the first 4 numbers, first 4 digits of the decimal and put ... So let's see if we can do something similar with question number 9. 3 to the x plus 4 equals 101. Well, you cannot just divide by 3. Dividing by 3 doesn't get rid of that base. A lot of people assume that that will happen, and it does not work that way. The only thing I can do to get to my variable, which is trapped up there in the exponent spot, is to go into logarithm form. So log base 3 of 101 equals x plus 4. If you recall, we should be able to do that swirl method and have it be the same thing as our problem, which I think it does actually work out. 3 to this equals that. So let's go ahead and do the change of base. Log of 101 divided by the log of 3. That's equal to x plus 4. To get rid of that plus 4, I'm going to need to subtract it, but subtracting always goes at the end of that big chunk right here. So let's go ahead and let's put that in my calculator and get my answer. So let's trap the big fraction part together. Logarithm of 101 divided by logarithm of 3. Trap those things together so that they don't mess around with your subtracting 4. Go ahead and enter, and I get 0.2008. This is the only number that would work right up there with the variable to equal 101. Hopefully you guys are getting the hang of it. Question number 10, very similar, except that we have e. E, if you recall, is just a number. It's about 2.7. Kind of like pi is about 3.14. If I go ahead and start to solve this, I got to get rid of the easiest stuff first. So that means adding 3 to get rid of the subtracting 3. So 2e, 4x minus 1 is my exponent, 15 plus 3 is 18. Divide by 2, get rid of that sucker. So I get e, 4x minus 1 equals 18 divided by 2 is 9. Now, e and 9, nothing in common. So I'm going to have to do logarithm form. So let's bring it up over here. I would write log base e. But when I get to that spot, something's ringing in the back of my head. I should know something about log of e. If I have log of e, it is just equal to the natural log. So ln. That says log base e. Now if I go ahead and swing it around town, 9's the next thing, and then I'm equal to my exponent, which was 4x minus 1. If I'm solving like this, just leave the natural log of 9 alone. It's a number, it's a decimal. If you're really concerned about it, it's right over here. Natural logs, are right under regular common logs, so I hit ln 9. Natural log of 9 is just 2.19. Okay, it's just a decimal. In order to solve the rest of this, I got to get rid of the extra stuff. So that means adding 1 and adding 1. So I have the natural log of 9 plus 1 equals 4x. Divide by 4, and when I divide by 4, you have to divide the whole side by 4. So x is going to equal probably some crazy decimal. Keep in mind, keep in mind this thing is all trapped together in the numerator, so I'm going to have to put parentheses there. So let's trap the natural log of 9 plus 1 all in the numerator. Divide that all by 4 and hit enter. My answer is 0.7993. Logarithms and exponentials are so important. Engineers and people who do electronics and things like that use logarithms a lot during the actual construction and manufacturing phase. So they're very, very important to know how to work with them. 11 and 12, the last ones on this page, similar in style. If you want to go ahead and try to work these out ahead of time, go for it and then check your answer with mine. If you still aren't comfortable, just follow my steps. So with 10, I'm adding 4 to get 10 to the x plus 3 equals 24. 10, 24, nothing in common. I can't get them to be the same base. So let's go ahead and let's change it to logarithm form. Log of 10, which reminds me that that's a common log, so you don't have to put the little 10 down there. 24 goes inside, and my exponent is always what it's equal to, x plus 3. So let's go ahead and let's get rid of the plus 3 by subtracting, and it comes at the end. It'll look something like this, 24 with a minus 3, and that's equal to x. Putting that in our graphing calculator. We can actually just use the regular log button. This is a common log. 24 goes inside, subtract 3 from that answer, and I get negative 1.6197. It's not bad. If you have a graphing calculator, something that can do logarithms or natural logarithms really easily, and that's why I really pushed and stressed for you guys to get your own graphing calculator. Regular calculators can do this too, so it doesn't necessarily have to be one of these fancy guys. Question 12, last one on the front. E to the 3x equals 4. There's no way e, which is 2.7, is going to work out to get a 4. So the bases option will not work. Let's try to go ahead and go to log form. Log base e. Ah, shucks, that's just a natural log. So we'll go ahead and change it. Natural log of 4 equals the exponent, which was 3x. In order to go ahead and get rid of the 3, you just divide. So I'm going to have the natural log of 4 divided by 3. Natural log 4 divided by 3 equals 0.4620. Again, dot, dot, dot at the end, because that number doesn't end. It's irrational. Hopefully you guys have a little bit of a better grasp here on solving exponential equations. Sometimes they're easy if those bases match up perfectly and you can just deal with the exponents. But there are other times when your answer is, especially if it's a decimal, you have to work with some logarithms, and that's why translating between the two is so important. If you got that, let's go ahead and let's flip to the back side of the notes, starting with question number 13. These are all logarithmic equations. Notice on your page, all of these problems have the word log in them, or maybe ln. That's just a logarithm, a special type. So when we're doing these, it's nice to maybe go back to exponential form, so long as the change of base formula doesn't work. Which in question 13, if we look at that, log base 2 of x equals 3. Well, if I tried the change of base, it would be log of x over log of 2, don't write this down, equals 3. Notice how my variable's still trapped. It's trapped within a logarithm, and that is not good. I want to break the variable free. So if I go ahead and get rid of all of this, what can I do? Maybe I can go to exponential form. So if you go back to exponential form, remember it's kind of that swirl idea. The base is 2, right there. The exponent is 3, and that's equal to whatever is inside parentheses, which in this case happens to be x. Now, once you see this, you're like, oh gosh, that's easy. 2 to the third equals x. Well, 2 times 2 times 2 that's just 8. 8 equals x. And that's your answer. That's all you have to do. So sometimes logarithms can look confusing until you look at them from the exponential side of things. So let's see if that works with 14. Maybe it does. So here we have log of x equals 36. Again, that change of base formula would look like this, and it does not get the variable out. It's still trapped inside, so we can't do that. Maybe trying the swirl method is going to be the best method here. So x squared equals 36. Well, how would I solve that? This is kind of a nice throwback to before Christmas. In order to get rid of a squared, you got to square root. Now remember, if there's an exponent inside, there are going to be 2 different unique answers. That happens because we get the absolute value of x. Square root of 36 is just 6. Now, how do we get rid of those absolute value bars? Well, with a plus or a minus. So there are technically two different numbers that would work. Now, just kind of keeping things in mind here, logarithms I don't believe are allowed to have negative bases. So technically, I think x can really only be 6, although with the work, we get 2 answers. So I'd just be happy if you get x equals 6. We're not going into some of that deeper math. If you would like to know why that doesn't work, you have to look at why exponential bases can't be negatives. You can't have negative 6 to the x because it blows up the graph. If you remember something about that when we were graphing them. So that doesn't work, and so the negative version won't work as well for logarithms. Number 15, log 2x minus 2 in parentheses equals 4. If you don't know what is down there, shame on you. It's a common log. That means it's a base of 10. So let's go ahead and let's see if we can swirl it around and get to exponential form. It looks like this. 10 to the 4th equals 2x minus 2. 10 to the 4th. What is that? 10 times 10 times 10 times 10 is 1 with 4 zeros. Kind of think about it. 10 squared is 100, 1 with 2 zeros. 10 to the 4th is going to be 1 with 4 zeros. That's 10,000 equals 2x minus 2. Then we have to work our way out. Add 2, add 2. I get 10,002 equals 2x. Divide by 2 and divide by 2. I'm really hoping your solving skills have sharpened and they're quick. 10,002 divided by 2 is 5,001. That's a big number. This is the only number that would work in here to make the answer equal out to be 4. Nothing else would work. Question 16 says log base 25 of 1/5 equals 3x. If I go ahead and do the swirl base here, 25 to the 3x equals 1/5, that doesn't help me out because now my exponent is trapped up there in the top. So you have to understand, you don't want it to be trapped in the base of a logarithm or inside a logarithm, just like you didn't want it to be trapped up in the exponent spot for the first side. So let's maybe try to do the change of base formula. In this case, log of 1/5 over log of 25. That's just equal to 3x. Oh, that looks actually a little bit better because I can get rid of the 3 fairly simply by dividing. Remember, that's on the bottom, so I have to put it on the bottom. If I type this in my calculator, log of 1/5, which is just 1 divided by 5, divided by, and I need to trap all of this stuff down there. So I'm not just dividing by 3, I'm dividing by both of those things. So put a parenthesis, put 3, put a time symbol, and put log of 25, close the logarithm, close the bottom. Go ahead and press enter, and we get negative 0.1666666 forever. You could also put negative 0.16 with a bar over the 6. It means the same thing. It means repeating. If you're really good at fractions, you would know that this is just negative 1/6. 1/6 repeating forever, 1/6. Kind of a handy hint. Question 17. 6 times the logarithm of 4x plus 2 equals 12. Start with the outside. Get rid of the 6. 12 divided by 6 is actually fairly nice. So I get log of 4x plus 2 equals 2 from right up above. In order to get rid of all this stuff and get into the x, I'm going to actually have to do the swirl. 10 to the 2nd equals 4x minus 2. It takes a little bit of experience. If you try something and it doesn't work, that's okay. Try something else. You can't hurt yourself unless you just give up. So 10 squared is 100 equals 4x minus 2. Get rid of that 2 by adding. Let's come up over here. 102 equals 4x. Just got to divide by 4 and divide by 4. 102 divided by 4 is 25.5. ln natural log. So you can think about this like the log of base e, almost. X plus 6 is inside, minus 3 is outside, equals negative 5. Well, start with the outside. Get rid of that by adding 3. So I have the natural log of x plus 6 equals negative 2. Now we have to think about this is e. So e, and if I swirl it around, e to the negative 2 equals x plus 6. All right. Seems like the variable's on its own side now, and I can just subtract 6. But the subtracting 6 goes at the other end. It does not go up with the negative 2. It's negative 6 is its own number. So I get e to the negative 2 minus 6 equals x. What does the negative exponent mean here? Remember, negative exponents mean that they jump to the other side of the fraction. So this is technically 1 over e squared minus 6. You don't need to know that, but I want to make sure that you remember things from the past. If we put this in, your calculator has a nifty little button. So e, you could use 2.7, or you could do second natural log. Notice e to the x is right there with it. So e to the, we could put in negative 2, just like what it says up here, and then subtract 6 as a big regular number after that. And I get this answer, negative 5.8646. Put a couple dots at the end, box it in, and you're done. Usually when kids are working on these problems, they get to 19 and then they just throw their pencil in the air. They're like, I don't want to do this. But it's actually not as bad as you'd think. If you look, it's log base 11, then we have some stuff inside, equals log base 11, and we got some more stuff inside. They're like, 2 logarithms? It's like, 2 rainbows? Double rainbows? Well, this is just double logarithms. Think about this. If we were going to do a problem on the front side of the notes, and it looked like 11 to the x equals 11 to the 3, aren't those bases the same? So the exponents have to be the same as well. Well, the word bases, you have to remember that's talking about a position. What are the bases for these logarithms? Well, it happens to be 11 and 11. So guess what we get to do if the bases of a logarithm are the same? Well, we get to set whatever is inside equal. So since they have the same base, set the insides equal. So set the insides equal and then just solve. It's not very hard in this case. It'll be 3x minus 7 equals 11 plus 6x. This actually might be one of the easier problems we've done on the back. Going ahead and getting the x's on the right hand side, getting the numbers on the other side, I get negative 18. Negative 7 minus 11 is negative 18 equals 6x minus 3x is 3x. Final step here of dividing to get rid of that coefficient in front of the variable. Negative 18 divided by 3 is negative 6. That's not bad at all. That's just a little bit of algebra and some algebra 2 understanding. Question 20. Moving right along. This is a common log, so think about the base here is 10. In order to get to the variable, I'm going to have to do the swirl method. Change of base won't work. So it looks like this. 10 to the negative 1 equals 7 minus 2x. 10 to the negative 1. Remember what it did up here. It makes that thing jump. So this is just 1 over 10 to the first, or just 1/10, equals 7 minus 2x. Now I got to get rid of the adding and subtracting first, so I need to subtract 7. So this is 1/10 minus 7 equals negative 2x. A lot of people forget about the negative right up here. It has to carry down. It has to carry down because when I divide by a negative 2. Go ahead, you divide this piece up there, all of that, by -2. So let's go ahead and let's see what that gives us in our calculator. I will take and wrap everything in the numerator together. 1/10, not 1/11, 1/10. Subtract 7, that's all trapped together. If you wanted to be really, really picky, technically you should wrap this in its own parentheses. The 1/10. See how 1/10 is its own thing, then I'm subtracting 7, but they are both together. Then we'll go ahead and we'll divide by -2. Since you're dividing by one thing, you can just put divide and put the -2 on the bottom. Hit enter, I get 3.45. So that's actually a nice number. You do not put ... at the end because your answer is nice and clean. 2 decimals, and it ends. Last 4 questions on the notes. Hallelujah. 21. Log of 125 equals x. Well, log of 10. If I think about this and I try to do the swirl, 10 to the x equals 125, that's not helping at all. But since I have a number here and a number here, the change of base formula will actually work. Log of 125, because that's the bigger number, it's towards the top, over the log of 10. That should equal x. I will share a little hint with you in a second. Change base. Log of 125, and divide that by log of 10. I get 2.096. .0969, excuse me. 4 decimal places, again, fairly nice. If you were smart and you saw that the problem looks like this, log of 125 equals x, can your calculator actually do that for you right now? Notice what happens when I put in log and then I put 125 in. That looks the same as the problem that was on my paper. What do you notice about those answers? They happen to be the same. So because it was a common log and because there wasn't any adding or subtracting over there, I could have just gotten the answer by putting that problem in my calculator. Crazy. 22. Question number 22. This is going to take the swirl to get the x, or the variable, out from that base position. So x to the third equals 27. This should look a little familiar from the front, but you have to remember how to solve for cubics, things that are cubed to that exponent. In order to get rid of a cubic, something cubed, I'm going to have to cube root. So those will blow each other up and you're just left with x. No absolute value bars. Don't do that because it's an odd number. Okay, a cube root is dealing with an odd. You'll never have i's or imaginaries with odd roots. The cube root of 27, well, that just goes down to what type of number 27 is. 3 times 3 times 3. I think I have enough to break out of this cube root prison. So in the end, x is equal to 3. If you didn't think about how to do that with the cube root, that's fine. I hope you're using your logic and you think a number tripled by itself times itself 3 times equals 27, and you know 3 times 3 times 3 is 27, you can just get straight to the answer. Number 23, the natural log of 4 equals x. Very similar to actually question number 21. If you realize this is something you can put in your calculator, go ahead and do that. Gosh, it's so easy because there's a natural log button. You just have to put 4 in there. Put the right type of parenthesis. Natural log of 4, natural log of 4, things match up. Press enter. That's your answer. I mean, if I put that on a quiz or a test, I'll give it some points, but I'm not going to give it very much points because I'm looking to see if you understand what to do. 1.3862. You should love those types of problems. Very easy. 24, is that the same thing? I think it is. So if we go ahead and just put that in our calculator, the natural log, since the variable isn't in the base or inside, I can just go ahead and put 7.389 parenthesis and hit enter. Look at what this number is. 1.999992408, blah, blah, blah. What is that really close to? It's actually really close to 2, and the reason it's not 2 on the dot is because this was estimated. It was rounded a little bit, so my answer is technically 2. All right, if you want to be specific, x is approximately 2. We give it like a sort of equal sign. You know, kind of like when you're waving your hand, it's about that. If you are a straight shooter, though, go ahead and put 1.9999. I will accept either of those. I frankly don't care. But the goal here, to get you to understand what's going on, we get 2 because we're approximating a little bit. I hope that this video helped you out. Again, if you need to rewatch it, you can always visit my YouTube page at home and go over problems that you are struggling with and get some advice of how to step through those different problems. Hopefully you're a little bit better than when you started. Remember to always ask great questions. We'll see you soon, guys.